Okay, in this problem, we're going to look at what happens when some event like a mass migration occurs and the supply of labor is increased dramatically, pulling down the wage rates, um, which then has an effect on supply because if wages fall, the marginal cost of production decrease generally, and a decrease in marginal cost of production is an increase in supply. So when this occurs, we're going to see an increase in the output firms expect to sell, which also is going to have a dual effect. The immigration is going to cause that and pull down wages. Okay. So the company, the firm, Burger Dude, is a chain of regional fast food restaurants. K is the number of burger robots it acquires, and L is the number of hours of human labor it hires to make burgers. So it uses robots and human labor to make burgers. Market and analysts have indicated to Burger Dude that the restaurant can expect sales of 1,058 burgers per hour. The 1,058 burger isoquant is graphed in figure 1. So anywhere on this isoquant meaning same quantity, anywhere on this curve, the company can make 1,058 burgers, right? The cost minimizing capital and labor combination, labor, capital, the cost minimizing level of capital and labor is 0.0, the original optimal solution. Costs are minimized at 0.0, and those costs total $8,246. Now, unlike the short run, where only labor can be adjusted, Burger Dude can add capital and labor over the long run. Therefore, whereas only labor is variable in the short run, all costs are variable over the long run. The equation for Burger Dude's total expenses is given below. Burger Dude's ISO cost line is found by solving the following for K. So this is the cost. This is the hourly cost per unit of capital. These are the units of capital. This is the hourly wage rate of labor, and this is the hours of labor. And when we solve that for capital, because K is the vertical axis and L is the horizontal axis, when we solve for that for capital, we get an intercept equal to the cost of these combinations of capital and labor, the cost, which in this graph happens to be 8,246. We're going to divide that by the hourly rate per unit capital. Then we're going to subtract off the slope times L, and the slope is the wage rate divided by the hourly rate per unit cost of capital, right? Now, according to the figure above, Burger Dude's production cost equal 8,246. Suppose Burger Dude hires from perfectly competitive factor markets at a cost of capital equal to $124 per unit. All right, I'm going to put the unit cost per hour of capital and labor in Desmos. So this is the wage rate, and this is the hourly cost per unit of capital, right? And then the cost, production cost in the graph were 8,246, right? So the intercept of the ISO cost line that corresponds to this cost is that cost divided by R. So if we do C divided by R, we get an intercept of 66.5. And then we get a slope equal to W the wage rate divided by the unit cost of capital, the hourly unit cost of capital. And so that is 0.1. Okay, so the intercept here, notice at the optimal solution, we got 33, we have 33 robots hired or acquired, 33 robots acquired. The intercept is 66.5. This number here corresponds to the cost along this ISO cost line, right? So this number is not the number on the vertical axis right here. It is the value at each point along this ISO cost line, right? Just like this is the value of quantity of burgers produced along this curve, right? Now at the capital labor ratio that minimizes Burger Den's cost, 0.0, Burger Dude acquires 33 hamburger robots and hires 335 hours of labor. 335 hours of labor. Though the marginal rate of technical substitution along the isoquant, as more labor is substituted for robots, the marginal rate of technical substitution does what? It goes to zero. So we're adding labor and reducing robots, right? So from this point along the isoquant curve, we're adding labor, reducing the number of robots we have, reducing the amount of capital, and the slope is changing, right? It's getting closer to zero. If we substitute robots for labor, right, the slope of this curve, called the marginal rate of technical substitution, gets increasingly negative. But as we substitute human labor for robot labor, the slope gets closer and closer to zero, right? So given that, the slope at 0.0, the slope here of the curve at 0.0, if you notice, in a really small neighborhood of O, the slope of the curve equals the slope of the isocost line. And the slope of the isocost line is 0.1. It's negative 0.1. All right, I had to fix that. So the marginal rate of technical substitution equals a negative 0.1. That value implies that Burger Dude needs to reduce its employees' hours worked by what if it wants to add one robot to keep output constant at, we're trying to keep output constant at what? 1058. Okay. So what we need to do here is we need to look at the marginal rate of technical substitution at 0.0, which equals 0.1, right? It equals 0.1 right there. The slope of the curve equals the slope of the line, 0.1. Okay. So this says the change in capital, and this is the change in labor. So this is the slope of both the isocost line and the isoquant line at the optimal point. And that's only true at one point. Both those things together are true only at one point, at the optimal solution O, right? And the slope of the isocost line is the W over the rate, the price of capital, unit price of capital, right? It's just that ratio. And that ratio is 0.1, right? W divided by R is 0.1. Okay, so because the slope has two parts, I'm going to delete this W over R. because the slope has two parts, a change in capital over a change in L, and our value is only got one component, I'm going to write the 0.1 as 0.1 over 1. Okay, so 0.1 divided by 1 is still 0.1, right? That's just a little trick. Okay. The next trick I'm going to do is I'm going to multiply the 0.1 divided by 1. I'm going to multiply that by 10 over 10. Now, this value is still what? The value is still 0.1, right? So I haven't changed the value of it all. It's still 0.1. Why is it 0.1? Because 10 divided by 10 is 1. And 1 times 0.1 divided by 1 is 0.1, right? Now it's just a matter of doing a little arithmetic. When you when you multiply two fractions, it's equal to the numerators multiplied by each other and the denominators multiplied by each other. So 0.1 times 10 is 1, and 1 times 10 is 10, right? So now I'm going to delete all this stuff and look at and interpret this value. So what this says is if capital changes by 1, labor is going to change by 10, right? And this is the absolute value because the slope is actually negative. So if capital changes by 1, labor is going to change by 10, right? So this value here, negative 0.1, implies that Burger Dude needs to reduce its employees' hours worked by 10 if it wants to add one robot to keep output constant at 1058, right? Now, with Burger Dude's total expenses equaling $8,246, and zero long-run economic profits are possible in the long run, so it cost her $8,246 at the cost minimizing level of capital and labor. So with Burger Dude's total expenses equaling that, and economic profit being zero in competitive markets over the long run, so profit is equal to price times quantity minus cost, right? And we're saying that profit is zero in the long run. Economic profit, not profit, but economic profit is zero in the long run, right? Then what we're saying is the costs have to be equal to the revenue, and revenue is price times quantity, right? So in the long run, our cost equal our price times quantity, or revenue, right? And then our price must be then what? The cost divided by output, right? The cost divided by output. So the firms, if this is zero, for this to be zero, revenue has to equal cost, right? So revenue is equal to cost, right? And the burger price must be equal to what? The cost divided by the quantity. With the cost being 8,246 and the quantity being 1,058, the price of the burger today is 7.79. The price of the burger is 7.79. $7.79. Okay. Now, suppose the government decides to eliminate immigration laws that limit migration from other countries. As a result, millions of workers migrate to the U.S. in search of a better life and increased economic opportunity. If hamburger cook positions are filled by low-skilled workers, and many of the new immigrants are low-skilled, the migration will have what effect? It will tend to push wages down for hamburger cooks, right? Now, after submitting this answer, the effect of this is shown on the graph. So I'm going to hit enter here. So we have a new isoquant, right? The firm is going to increase its output from 1058 to 1430. Well, why is that? Well, what I said earlier at the beginning of this video, when wages come down, marginal cost of production shifts downward. It decreases, right, for a given quantity. A decrease in marginal cost is an increase in supply. So firms are going to scale up, right, holding all other factors constant, right? And we learned that in micro principles, right? So the graph indicates that the firm now expects to sell how many burgers? 1430, right? This effect resulted in the market wage falling to $6.08 per hour. So the market wage rate was $12.40. Now the market wage rate is $6.08. You used to have a lot more people supplying their labor to hamburger joints. It pulls the wage down. That labor is less scarce, and things that are less scarce, their value per unit decreases. Now, since the lower wage does what? The lower wage does what to our isoquant? Our new wage is $6.08. So I'm going to change this to $6.08 an hour. What happened to our slope? Our slope is now 0.05 or 0.049, right? So our slope is a lot lower. So our slope is doing what here? It's flattening. The decrease in the slope is flattening the isocost line, right? This isocost line is too steep. So the new isocost line is going to be flatter, right? So the effect of the wage rate falling to 6.08 flattens the isocost line. Okay, at 33 hamburger robots and 439 hours of labor demanded, the Burger Dude's cost is equal to what? Let's calculate it. So we have 33 hamburger robots at a price of $124, plus we have 439 hours of labor at a new price of $6.08. $6.08. So Burger Dude's cost is equal to what now? To 0 decimal places, it is equal to $6,061, $6,700.61. Or sorry, $6,761, right? Yep. Now that submitting that answer graphs a new isocost line, right? That isocost line is flatter than the original isocost line, right? Now notice anywhere on this isocost line, there's no place on this isocost line where we can produce 1,430 units of burgers, right? There's not one point. So this is not feasible, right? So what do we do? Maybe we adjust our capital and our labor to what? 32. Now we're going to make capital. Oh, yeah. So there is no combination of capital and labor on this isocost line that can produce the 1,430 burgers we expect to sell now, right? We expect to sell 1,430. And we can't produce that with this capital labor ratio, right? That combination of capital and labor. Let's try 32 hamburger robots and 542 hours of labor, right? The burger dude's cost is equal to what now? Well, to 0 decimal places, it's equal to $7,263. Okay, now the ISO cost line moved out a little bit, right? It got closer to our ISO quant curve, right? It got closer, but it still doesn't touch it yet, right? And for that reason, they're not going to choose 32 robots and 542 hours of labor, right? They're not going to choose that because there's no combination of capital labor on this new ISO cost line that can produce the 1430 burgers we now expect to sell, right? Okay, so we continue to adjust capital and labor until we get to a point on the isoquant curve, point F. And at point F, labor hours is 646, and it looks like capital is 32. It's kind of hard to see there, but if you look at the red, 32 is just below 33, so it's 32, right? So the cost minimizing levels, according to the graph, is 32 robots. And what was it? 646 hours of labor. Okay. Now notice when we press enter, we get this new ISO cost line, right? We get this new ISO cost line here that is just tangent to this isoquant, the new isoquant at point F. And the cost is 7,896. Whoops. That's how many burgers it's producing, right? At this capital labor ratio, Burger Dude's producing 1,430 burgers at a total cost of $7,800, $7,896. Right. So the cost is $7,896 at this capital labor ratio of 32,646. And it's making 1,430 burgers, right? Okay, since economic profit is $0 in a competitive market over the long run, right? The firm's revenue again has to be equal to its cost, right? Revenue minus its cost is a zero economic profit over the long run, right? So what does the price of the burger have to be now? Well, now the cost is 7,896. The output is 1,430. So the price of the burger fell to $5.52. Okay, now the decline in the wage rate has two effects. Because it lowers the price of labor, the firm feels compelled to expand its operation. Recall the effect of a lower wage in microeconomics. A lower wage reduces the marginal cost of production, which represents an increase in burger supply, right? We mentioned that earlier, right? So click submit to observe the output effect, right? It's going to be a shift from point O to this new point H, which is not modeled yet. So I'm going to hit enter here. So I have O to H, right? We have this output effect. So when you go from O to H, you ignore the change in the wage. And so the firm is going, all right, we need to make, with this now new lower wage, we're going to stop making 1,058 burgers per hour. We're going to make 1,430 burgers per hour, right? So we're going to need, if we do that, we're going to need to increase our labor from 335 to 452, right? So we're going to need 400, we're going to demand 450 hours of labor if we ignore the change in the wage, right? And just look at the increase in output. So we're going to ramp up our labor demand to 452, and we're going to ramp up our hamburger robots to 45. So we're going to require 45 hamburger robots and hire 452 hours of additional labor, or of labor total, right? That's the output effect. Okay. Now the substitution effect comes into place, right? The substitution effect is the slide from point H down to point F. And when you slide down this isoquant, the slope is changing. The slope at point H is the same as the slope at point O, right? Because you're going to see this in a second. We're going to have a parallel shift in the isocost line. Sliding down this isocost changes the slope, right? So the slope can change by either the price of capital changing or the wage rate changing. And in our model, the wage rate is changing, and we're holding the unit price of capital constant, right? So we're going to get a slide from green down to blue, right? And that's going to model the substitution effect. As we slide from point H to point F, we're going to reduce this capital demand from 45 down to 32, right? And we're going to increase labor from 452 to 646, right? The output effect, when we have the output effect here, both capital increase from 33 to 45, and then labor increase from 335 to 452. So the output effect, both factors increase in demand, right? The firm is demanding more of both of these factors in the output effect. But in the substitution effect, we are substituting away from robots and adding labor, right? So we have a substitution from H to F, right? So holding output constant, right? Holding output constant, our new output constant at 1430, holding it constant at 1430, right? The substitution effect is the slide from point H to point F. And it models the effect of the falling wage on Burger Dude's capital labor ratio, right? So you can see this green isocost line, right? This green isocost line, like I said, is parallel to the original isocost line, right? They're never going to intersect, are they? They're never going to intersect, right? So because the green line and the black line are parallel, we're assuming the wage is the same at both H and O, because we're holding R constant, right? So when we move from O to H, we're holding constant the wages that we pay and the unit price of capital that we pay. We're holding them constant, right? So we have this output effect from O to H, right? Now from H to F, the slope changes from the green slope to the red slope, right? And that's again because the wage rate fell, right? The wage rate fell. Okay, according to the graph, the cost of this level of burger production would equal what? At point H, right? What's the cost of burger production at point H if we were to implement point H. If Burger Den implemented point H, how much would it cost? It would cost $11,185. Now, if you don't see it on the graph, you can calculate it, right? At point H, which is labeled H because it's hypothetical, we don't really observe it. Capital is 452. All right, so labor is 452. And at H, the slope is the same as the original isocost line. So the slope hasn't changed. The wage is assumed to be the same as it was at the start of the problem. So $12.40 per hour. Capital is 45 at point H. And capital costs 124 per unit, right? So the cost at point H, assuming prices haven't changed, the unit cost haven't changed of these factor inputs, is in fact 11,185 if you round to 0 decimal places, right? That 8 makes that a 5, right? So that value is correct, right? And that's how you'd calculate it if you don't see it up here, right? Now, the problem with this is, what's the cost at point H? I mean, what's the cost at point F? At point F, the cost is what? It's much lower, 7,896, right? So we're not going to choose H. H costs too much, right? H costs too much. Point F is cheaper. Point H is more expensive, right? It's more expensive. Also, point H is not possible because point H is calculated with the old wage rate, right? It's computed with the old wage rate of $12.40 per hour, right? All right. Now the output effect is what labor demand does from the original optimal solution to the hypothetical optimal solution, right? What did labor demand do? Well, when we go from point O to H, if we were to go from point O to H, labor would start at 335. Labor demand would start at 335. Initial labor demand was 335. Final labor demand, quantity of labor demanded, is 452 at point H. That is the output effect on labor demand, right? The substitution effect is from H to F. So labor hours of labor demanded at point H is 452, right? And because the wage falls, we're going to reduce our, we're not going to demand 45 robots. We're only going to demand 32. And we're also going to demand 646 units of labor, right? Okay. So we could actually graph labor demand over the long run. We don't actually observe, like I said, the 452, right? We don't observe that, right? So labor demand increased from 335 to 646, right? So we can actually come up with an equation of that, right? We can come up with an equation. Well, the points of such a labor demand curve would be what? The original point had a labor of 335 at a wage of what was the original wage? 12.4, right? Where's that point at? There it is, right there. Okay, that's the original quantity demanded for labor at the original wage, right? We ended up where? We ended up at a different point where labor demanded was 646 at a wage of what? The new wage was, as a result of the immigration, the new wage where is it at? Okay. Here it is. The new wage is 608, right? Okay, and then we'll label it. Okay, let me stretch this. Let me stretch the y-axis. We'll do 10 and -1. Okay, so you could draw a line from this point to that point, and that could represent long run labor demand, right? Which makes sense because as the price of labor falls, the company demands more and more labor. Okay, so I went ahead and created a line, derived a line that pretty much fit both the initial labor demand, quantity of labor demanded by the firm when the wage was 12.4, and the final point that corresponds to the final amount of labor the firm demands at a wage of 6.08, right? And you can see it's downward sloping. So this black line would be called the labor demand equation, right? And the vertical axis is the wage rate, and the horizontal axis would be the hours worked.